Number 25. The engine of a Ferrari sports car takes in air at 20 degrees Celsius. So number 25, it takes in air at 20 degrees Celsius. So let's say T1 equals to 20 degrees Celsius. And 1 atmosphere. So pressure is 1 atmosphere. And compresses it adiabatically to 0.09 times the original volume. So V2 over V1, that's what they're really telling you, is 0.09, 0000. So the air may be treated as ideal gas with gamma equals to 1.4. So draw the PV diagram for this process and find the final temperature and pressure. So remember, this is adiabatic, so write down the process is adiabatic and it is ideal gas. So there are a few things that you need to write down so that you know what formula you can use and not use. So first they want you to draw the PV diagram. So PV diagram looks somewhat like this. First thing you do is you draw some isothermals from low temperature to then higher temperature. Okay, so this is high temperature, medium temperature, low temperature. Now, if the volume is compressed to 0.09, that means it started with a large volume and only became less, say 9% of the original. So if I were to assume that this is the V1, and this is only 9% of V1, so let's say V2, which is 9% of V1, and you start out with some 20 degrees Celsius pressure, temperature, so this one will be somewhat like for a low temperature, T1, and then this will be like a high temperature, T2. So basically, adiabatic compression in this case will be following the line somewhat like this. Towards this end. So this will be the adiabatic compression. Okay, so put an arrow showing that this process from V1 to V2, or from this state to that state. So that's the first part, to graph the PV diagram. Part 2 says find the final temperature and pressure. Final temperature and pressure. Now, because this is adiabatic, which means no heat exchanged, and also it is ideal gas, so you need to remember some formulas that associate with ideal gas adiabatic, and that is T1V1 to the gamma minus 1 is equal to T2V2 to the gamma minus 1. So that's the first formula. Second formula is P1V1 gamma equals to P2V2 to the gamma. So, and then you can now write down what P1V1 should be. Since we're looking for P2 and T2, that is the final temperature and pressure, so I'm going to isolate the T2 and P2 from these two formulas. The first one will be T1V1 to the gamma minus 1 divided by V2 to the gamma minus 1 will be T2. Or you can rewrite this one as T1 bracket V1 over V2 to the gamma minus 1. T1, you're told, is 20 degrees, but you have to convert that to Kelvin. So 20 plus 273.15. And then V1, in this case, to V2. Well, this is V1 to V2, not V2 to V1. So you just write the reciprocal. To the gamma minus 1. Gamma is 1.4 minus 1 is 0.4. So once you punch in the calculator, 293.15 times bracket 1 divided by 0.09 to the power of 0.4. I get a temperature of 768 Kelvin. So minus 273.15, I get 495 degrees Celsius. So that is your first answer for final temperature. And then final pressure, it can be done the same way using this formula. So P2 is what we want. So we say P1V1 to the gamma divided by V2 to the gamma, or you can write P1 times V1 over V2 to the gamma. And V1 over V2, we already said is a reciprocal of V2 over V1. So we can write 1 over 0.09 to the power of gamma, which is 1.4. and P1 is 1 atmosphere. So you can leave the answer in atmosphere in this case, because we're just doing the ratio. So 1 divided by 0.09, then raised to the power of 1.4. So my answer should be in atmosphere. So here is the final temperature, 495 Celsius. Here's the final pressure, 29.1. Well, I think their answer is wrong at the back of the book, which says 2.62. It should be 29.1. Okay, number 27. Adiabatic expansion. During an adiabatic expansion, the temperature of 0.45 moles of argon. So 0.45 moles of argon. Now argon is monoatomic. Drops from 50 degrees Celsius to 5 degrees Celsius. So T1 is 50 to 73.15 Kelvin to 10 degrees Celsius to 73.15 Kelvin. So the argon may be treated ideal gas. So here I'm going to write down the process is adiabatic, and it is an ideal gas. Okay, so we can write those two down. First, draw a PV diagram for this process. So similar to the previous one, you draw the isothermal first. So this is high temperature, medium temperature, low temperature. So in this case, it is from 50 to 10. So it's from high temperature to low temperature. If it's from high temperature to low temperature, well, it could go from here to here or from here to here. But you just have to cross these two. Now, but the question in 27 says, it is adiabatic expansion. So expansion means that the volume is increased. Therefore, between these two, the volume is increased, so it must be from left to right, which is high temperature from here to a low temperature to here. So the process must therefore look, adiabatic process must therefore look somewhat like this, where the arrow is pointing from this point to this point. So that is the PV diagram. So this is your T1, this will be your T2. That is adiabatic expansion. So part B is how much work done, how much work does the gas do? Well, the gas will do work if it is positive, and that will be the area underneath the curve here. So that is area, the work done. However, this is an ideal gas, adiabatic. So in terms of work done, for adiabatic ideal gas, well, you can use the formula of 1 over gamma minus 1 times P1V1 minus P2V2, or you can use the formula of NCV, T1 minus T2. Okay? But for argon gas, you can look up the CV for argon gas, which according to the table for argon is CV is 12.47. So this is 12.47, and number of moles is 0.45. Initial temperature is 50, well, minus final temperatures, so I could just use 50 minus 10. So if I punch in the calculator for all that, that will be the work done by the gas to the environment. 12.47 times 40. I get a 224.5 joule. So that is the amount of work done by the gas to the environment. And then they say, so does the heat flow into or out of the gas? Well, adiabatic means there is no heat flow. So this is part A answer. Part B answer is no heat flow because it's adiabatic. What part C is, what is the change in the internal energy of the gas, delta U? For adiabatic, delta U is minus W. So W is 224, so the answer is negative 224.5 joules. And that is the answer for part C. Okay, number 29. The question says the quantity of sulfur dioxide occupies a volume of 5 times 10 to the negative 3 cubic meter at a pressure of P1 is 1.10 times 10 to the 5th Pascal, and the gas expands adiabatically to a volume of, so V2, of 1 times 10 to the negative 2, or 10 times 10 to the negative 3 cubic meter. So now they want to know if the gas is ideal, what is the final pressure? So question number A is, what is P2? Question number B is, how much work is done? W equals to what? And part C is, what is the ratio of the final temperature to its initial temperature? Was T1 over T2 equal to? Remember, this is adiabatic. So whenever you hear the word adiabatic, you should remember several formulas. The number one formula is Q will have to be 0 for adiabatic. Therefore, change in internal energy plus work done must be 0. Or you can say that work done is the breakdown of internal energy. Okay? So that's the first formula. The second thing you should remember, that delta U by itself is N CV delta T. That only depends on the change in temperature. Okay? So this is only depends on change in temperature. But the question first is, what is the P2? So these formulas won't help you much, but you have to remember the second formula, and that is P1V1 to the gamma equals to P2V2 to the gamma. That is only applicable for adiabatic processes. And then the third formula is T1V1 to the gamma minus 1 is T2V2 to the gamma minus 1. All these require you to know what gamma is. Now, since you're told this is sulfur dioxide, so you need to look up what sulfur dioxide's gamma is. Now, it has to be given to you or provided by a table. And turns out that either they provide it to you, which is 1.29, or you look it up for sulfur dioxide. Therefore, we'll use that one to figure out what they want. Since you're given volumes already in terms of a ratio, so and then P1, so it looks like this formula is most applicable. So to figure out P2, we'll use this formula. So P2 is all this divided by V2 to the gamma. So P1 V1 to the gamma over V2 to the gamma, which is same as P1, V1 over V2, all to the gamma. And P1 is 1.10 times 10 to the 5th. V1 is 510 to the negative 3 divided by 10, so basically it's 5 over 10, because 10 to the negative 3 cancel, to the gamma. Now gamma is 1.29, so 1.29. So if you figure all these out, 1.1 to the 5th times 0.5 to the 1.29. So I get 4.50 times 10 to the 4th Pascal. So that's P2. And then, so that's P2A. And what is the work done? Well, the work, as we said before, is negative NCV delta T. But we have no time, we have no temperature given here. So one way is to replace NCV in terms of gamma. Okay? So for example, if you memorize the formula, is okay. If you haven't memorized the formula, then you can do it this way. NCV, there's negative, so it's supposed to be T2 minus T1, but now because of negative sign, I'm going to write T1 minus T2. But then CV times NT1 minus NT2, you could write it like this, is the same as, well, this is almost the same as PV over R. So T1 can be rewritten as PV over R, and then NT1 would be PV over R, like this. So I can now factor out the R, CV over R, P1 V1 minus P2 V2. But CV over R, if you recall, is same as 1 over gamma minus 1. So you may have to remember that. So this is the same as 1 over gamma minus 1. P1 V1 minus P2 V2. So that's the work done by adiabatic processes. So if you plug in all the numbers, you get 0.29. P1 is 1.1, 10 to the 5th. V1, 5, 10 to the negative 3, minus P2, we just figured it out, is 4.5, 10 to the 4th, times V2, which is 10, times 10 to the negative 3. So it all turns out to be 345 joules. So 345 joules is the work done. That is, the system does work to the environment. Okay, and then that's part B. And part C is what's the ratio of temperature? Well, that you can get from this formula. They want T2 over T1. So that ought to be V1 to the gamma minus 1 over V2 to the gamma minus 1. Okay, to bring this down, bring that down, which is same as V1 over V2 to the gamma minus 1. We already know what V1 over V2 is, which is 1/2 or 0.5. To the gamma minus 1 is now 1.29 minus 1's 0.29. So 0.5 raised to the power, or 0.29, I get 0.818. And therefore, T2 is 1 times 0.818, or the ratio is just 0.818. So that is part C. Okay, so that's the answers for question 29. The book has, anyway, in my edition of the book, they actually gave you a wrong information in the text. It says it is doing 285 joules of work. No, they should not have indicated that, because they were actually asking you what the work is in part B of the question. So they should not have provided you that answer or that information about that the gas is doing 285 joules of the work to its surrounding, and yet still asking you what is the energy of the work done to the surrounding, as in part B. Because if that was right, then you didn't even have to do any work here. You would just answer whatever they provided you. But then whatever they provided you would not work out to be the same as this number. Anyway.